All right, so a lot of NMR comes down to pattern recognition. You see these, different peak splittings, and then you can identify, oh, that's probably an isopropyl group or something like that. So let's go over some common patterns that we'll see. And so these are fragments of molecules that could show up separately from other compounds, right? So maybe they're located on some kind of aromatic group where we just have this R group here, and that's not going to couple with anything else. Or maybe it's on the side of an ether, right? So we have this fragment of carbon chain that's not going to couple with anything else. Or maybe it's on a nitrogen, right? Where it's not going to couple with anything else. Or maybe it's on an aldehyde, or maybe it's on an ether, right? Either way, you can see that these, in terms of proton NMR, are going to be independent of other parts of the molecule. And so if you see these patterns, this should be kind of a red flag. Oh, I have this type of compound. And so probably the easiest to spot is going to be tert-butyl, right? So here we're talking about what R is equal to here. And so if we think about a tert-butyl here, we've got 3 CH3s that are all connected to this quaternary carbon. And so this carbon doesn't have any hydrogens on it. And so what this shows up is just one giganto 9 hydrogen singlet. So if you see a 9 hydrogen singlet, you should be thinking, oh, I probably have a tert-butyl group somewhere in here. Similar to the tert-butyl is just a methyl group, right? This will be very similar to the tert-butyl, except it won't be as big, right? Instead of being 9 hydrogens, it'll integrate to 3 hydrogens. Another common one is isopropyl. And so if we think about our isopropyl group, we have something like this. And so we have 2 CH3s here. And then we have a single H right here. And so if we think about the splitting of this, the 6 H's will split into a doublet because they have one neighbor, and it should integrate to 6 hydrogens. And then the 1 hydrogen by itself will be a multiplet or a septet. So let's see if I can draw this. 1, 2, 3, 4, 5, 6, 7, right? It'll look something like that. It should have 7 peaks on it. So if you see something, then it should integrate to 1 hydrogen. So if you see something like that, that means you have an isopropyl. Ethyl will be another common one. So we have these H's here, and then we have a CH3 here. And so what you should see here is a 2H quartet corresponding to those hydrogens, right? They've got 3 neighbors. And then the methyl or the CH3 group here will have 2 neighbors. And so it'll split to N+1 peaks. It'll split into a triplet. And it'll correspond to 3 H's, right? If you see that there, then you probably have an ethyl group. And you can continue this on, something maybe like a propyl group as well. That's relatively common. You have 2 hydrogens here, 2 hydrogens here, and then 3 hydrogens here. These 2 hydrogens in the orange have 2 neighbors, so they'll split into a triplet. The purple have 5 neighbors, and so they'll split into a sextet. And then in blue, these 3 hydrogens have 2 neighbors, so they'll also split into a triplet, right? This triplet will be slightly larger than the 2H1 because it's as an additional hydrogen on there, right? And so you just want to look at these patterns and be able to spot them relatively easily. So let's take a look at an NMR type of problem that you might see. So let's say I'm going to give you the formula. It's CH14O. And so before you even start looking at the NMR spectra, the first thing you want to do is calculate your degrees of unsaturation, right? See how many pi bonds or ring systems that you have here. And so in this case, I'm going to go ahead, you can plug it into the equation, right? You should get 1 degree of unsaturation, right? If you think about this, 7 carbons, they can have up to 16 hydrogens. This only has 14, so you're missing 2, so you have 1 degree of unsaturation. And then you can also take a look at different types of stuff. So maybe you take a look at IR spectra and you see a big peak around 1700, right, that'll tell you that you have a carbonyl, right? And so now you've gone ahead and used up your degree of unsaturation. So after you've taken a look at that data, then you can start probing around the NMR, right? So maybe this is what you see in this NMR. And so the first thing you want to do is measure the relative peaks. In this case, I'll tell you it's a 1:6 ratio. And so 1:6, if we take a look at our structure, we can see that we have up to 14 protons, right? So 1:6, 1 plus 6 is 7. So that can't represent 1 and 6 protons. We actually have to double it, right? Because we have to have 14 protons total. And so this is probably a 2:12 ratio, right? That'll add up to 14 protons. And so that tells you that we have some kind of symmetry in the molecule because we have a lot of components represented by a small amount of peaks. And so then if we take a look at these peaks, let's figure out what they are. If we take a look over here, we can see that this is a doublet. So it's a 6 to 12H doublet. And then over here on this peak, we can count 1, 2, 3, 4, 5, 6, 7. 7 peaks. So it's a septet. So this one has 1 H neighbor. And this one has 6 H neighbors. And so if we take a look at our common motifs, the thing that you'll notice is that this perfectly corresponds to an isopropyl group, right? A 1:6 ratio where you have this big multiplet here with 7 peaks, and then you have a 6 hydrogen peak that's a doublet, right? And so we know we have an isopropyl group here. And then because this corresponds to 2 and 12, we know we actually have times 2 of them. And then also from the IR, we learned that we have a carbonyl as well. And so if we think about how many carbons and hydrogens we've used up, right? We've used up 1, 2, 3 carbons times 2 is 6. And then this will be our 7th carbon. So we've used up C7. If we think about all of our H's, we've got 3, we've got 6, we've got 7 times 2 is H14. And then finally, we've used up our oxygen here in this carbonyl. And so with these fragments of our compounds, we formed C7H14O, C7H14O. There's no more missing pieces of the puzzle. We just have to put them together. And so the only way you can put these together to make sense is to put the carbonyl in the center and then have 2 isopropyl groups right there. And so it's always then useful to reverse kind of engineer your final product, right? See what you would have. And so you'd expect, oh, I have these 2 H's, they're chemically equivalent. So I should have a 2H, and they both have 6 neighbors. So I should have a 2H septet. That's closer to my carbonyl, so it should be more to the left, right, to the de-shielded downfield portion. And then I have these CH3s here that correspond to 12 H's. They both have 1 neighbor, so it's a doublet. And it's further to the right because it will be more shielded because it's further away from the carbonyl. And you can see that exactly what you would predict is exactly what you would get. And that's how you figure out the carbon NMR. But really, it comes down to practice, 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 because that's what's going to help you with this pattern recognition.